We're going to be taking a look at zeros and turning points. Just a refresher, remember zeros are the same as your x-intercept. So if we had f of x equals x squared plus 8x plus 7, we wanted to find the zeros. We just replace our y with 0, because remember that's how we find our x-intercept. And then we could go ahead and factor this to solve. So we'd get 0 equals x plus 7, x plus 1. And we'd get our zeros at x equals -7 and -1. So these would be our zeros. All right, a new concept, but pretty easy. I just wanted to show you what a turning point is on a graph, and it's pretty self-explanatory. If we had a graph like this, boom, we turn, that's a turning point. Boom, we turn, that's another turning point. Boom, boom, 2 more turning points. So all of these spots where the graph changes direction are turning points. So we've been working with polynomials and the degree of a polynomial. Remember, the degree of a polynomial is just you take the biggest exponent in the whole thing. In this case, we'll just say it's n here, and we'll say this polynomial has n degree. The degree of the polynomial can tell us a lot about zeros and turning points. So a polynomial with degree n has at most n zeros and n minus 1 turning points. So this is the maximum number of zeros that a polynomial can have, and the maximum number of turning points a polynomial can have. Let's just do some quick examples. So this polynomial here, f of x equals 3x to the 5th minus 2x to the 4th plus 3x squared minus 2, has a degree of 5, because 5 is our biggest exponent. So since the degree is 5, we have a maximum number of zeros of 5, and we have a maximum number of turning points of 5 minus 1, which is 4. Here we have f of x equals 1 plus 2x minus 3x cubed. Now pay close attention here. The degree, the leading term here, is not 1 even though it's in the front. We have to pay attention to the biggest leading term here, and our power here is 3. So this is our leading term. Now our degree is going to be the biggest exponent of 3, which means that we're going to have a maximum possible number of zeros of 3, and we're going to have a maximum number of turning points of 2, 3 minus 1. In this problem, we want to state the number of possible real zeros and turning points of each function, then determine all the real zeros by factoring. So let's start by stating the number of possible zeros and turning points. Here we have a degree of 3, so we know we have a maximum possible number of zeros of 3, and our turning points is going to be 3 minus 1, which is 2. Okay, next, to determine all the real zeros, we need to go ahead and factor and set this equal to 0. So I'm going to go ahead and set this equal to 0 here. Looking at my function, I see that they all have an x in common. So I'm going to factor out an x. That's going to leave me with x squared minus 6x minus 27. I can factor further. This is going to go ahead and give me 0 equals x minus 9, and x plus 3. Now that I'm fully factored, I know that I'm going to get my zeros. Here are my different zeros that I'm going to have. I'll get my zeros of 0, positive 9, and negative 3. And I just got those by solving, setting each of these equal to 0. Let's try another one. Here we have f of x equals x to the 4th minus 8x squared plus 15. I see I have a degree of 4, so I know I have a maximum possible number of zeros of 4. My turning points is going to be 4 minus 1, which is 3. Alright, now let's go ahead and factor this out. Whoa, I am so glad I chose this problem because it gives me the chance to show you something new. It's really just a spin on an old trick, but here we have x to the 4th minus 8x squared plus 15, something we previously could not factor. I'm going to show you how to factor that right now, so make close note on this one. Let's say we had a function x squared minus 8x plus 15. You say, Mr. Zonker, I can easily factor that. That would just be x minus 5, x minus 3. Now we can see these are very similar here, but instead of an x squared, we have x to the 4th. Here, instead of 8x, we have 8x squared. So what we can do here is when we factor this out, instead of having x minus 5, we're going to have x squared minus 5. Instead of having x minus 3, you guessed it, we'll have x squared minus 3. Now this is the case because this x to the fourth and x squared have kind of a similar relationships as this x squared and this x. And if we FOIL this out, we'd get right back to here. So whenever you have this case x to the fourth and an x squared, you can factor like normal, but instead of just an x here, you're going to have an x squared. Alright, let's go ahead and just set this equal to 0 and continue on. To solve each of these, we want to put each of these equal to 0, so we'll get x squared minus 5 equals 0. Here we'll get x squared minus 3 equals 0. I can add 5 over. That'll give me x squared equals positive 5. Add 3 over, x squared equals positive 3. Take the square root of both sides. Remember, when you square root, you have to plus or minus. So we get x equals to plus or minus 5. Here, when we square root, we're going to get x equals plus or minus the square root of 3. And these are going to be our zeros down here. So we have 4 zeros, which we know is the maximum possible number. 2 of them which are plus or minus square root of 5. And here we have the positive and negative of square root of 3. Last thing I want to talk about is multiplicity. Multiplicity just basically means how many times a zero is repeated. For example, let's find the zeros of this function here. If we factor it, we'd get x plus 2, x plus 2. And if we solved for each of those zeros, we'd get x equals negative 2. And we get x equals negative 2 once again, because this is x plus 2 and x plus 2. Both of those zeros are going to be negative 2. So in this case, we have a zero of negative 2 that has a multiplicity of 2 because it occurs twice. Here we've got f of x equals x squared, x plus 1 cubed, and x minus 5. Think of if we rewrote this without exponents. Here we'd have, instead of x squared, we'd have x times x. Instead of x plus 1 cubed, we'd have x plus 1 times x plus 1 times x plus 1 and x minus 5. Now if we solved for each of these zeros, we'd get zeros at x equals 0 for this one, another 0 for that one. We'd have a negative 1, a negative 1, and a negative 1. Negative 1, negative 1, and a negative 1. And then for this one, we'd have a positive 5. So, writing these zeros in terms of multiplicity, we would have zeros of 0 with a multiplicity of 2. We'd have a negative 1 with a multiplicity of 3. And we'd have a 5 with a multiplicity of 1, but we don't need to write that out. So, often you're going to end up with pre-factored, or once you factor the form, but there's going to be more than one 0 repeated. So just know that that means it has a multiplicity of more than 1, and the multiplicity is equal to just how many times you get that same 0.